Episode 81, titled Mobile Attack Concepts, we frame mobile security risks around three practical lenses: where data lives, what permissions enable, and what the device posture says about the trust you can place in the environment. Mobile platforms give us convenience, sensors, and constant connectivity, but those same features create a dense attack surface that often gets underestimated. A disciplined way to think about risk is to follow the data, inventory the privileges, and assess the condition of the device that is enforcing or failing to enforce security boundaries. When you approach mobile assessment this way, you avoid getting lost in platform trivia and instead keep your attention on how compromise actually happens. That mindset is especially helpful for Pen Test Plus because the exam expects you to reason through risk rather than memorize a single tool or trick. Mobile data storage is the first major area where real-world exposure shows up because apps inevitably persist information beyond a single screen. Local files can include exported reports, downloaded documents, or media that the user assumes is private, and those artifacts often remain long after the user thinks they are gone. Caches and logs are particularly troublesome because they are created for performance and troubleshooting, not confidentiality, yet they can contain identifiers, requests, and even full payloads. Backups add another layer of risk, since data may be copied into cloud or desktop backup workflows that are outside the app's direct control, multiplying the number of places sensitive material can appear. When you evaluate storage risk, you are looking for what is stored, how it is protected, how long it persists, and how easily it can be accessed by another app, a user with elevated access, or an attacker with a foothold on the device. Permissions are the next lens, and permission abuse is often less dramatic than malware headlines, but more common in practice. Many apps request access that exceeds what is necessary for their core function, and users frequently approve prompts because they want the feature to work and the prompt feels routine. Excessive permissions widen the blast radius of a compromised app because a single vulnerability can turn into access to contacts, photos, location, microphone, or messaging data without additional hurdles. Even when an app is not explicitly malicious, overbroad permissions can enable privacy leakage through analytics, ad libraries, or poorly controlled sharing to other components. Conceptually, the security problem is simple. Every permission is a capability, and every capability becomes a potential path for misuse if the app is exploited or if its dependencies behave unexpectedly. From an assessment standpoint, the most meaningful question is whether each requested permission has a clear justification tied to a user-visible function. Insecure communications is another recurring theme, and it shows up both in encryption choices and in certificate handling behaviors. Weak encryption might mean outdated protocols, poor cipher selection, or homegrown cryptography that looks secure but fails under analysis, and the practical outcome is that data in transit becomes readable or modifiable. Unsafe certificate handling is often the bigger problem because developers sometimes disable verification during testing and accidentally leave that behavior in place, or they implement pinning incorrectly and create bypass conditions. If an app accepts invalid certificates, trusts user-installed certificate authorities indiscriminately, or mishandles hostname validation, an attacker can interpose themselves and manipulate traffic even when the user sees secure indicators. The key idea is that transport security is not just about turning on encryption. It is about correctly authenticating who you are talking to. When authentication of the remote endpoint fails, encryption can become a false sense of safety. Device posture is the third lens, and it matters because the security assumptions of a mobile platform depend heavily on integrity. A rooted or jailbroken device changes the threat level by weakening or removing controls that normally isolate apps and protect system resources. Sandboxing, file permissions, and key storage may still exist in some form, but the attacker's ability to observe, manipulate, or extract data becomes dramatically easier when they can run with elevated privileges. Even without full rooting or jailbreaking, posture can be degraded by outdated operating systems, insecure developer settings, side-loaded applications, or compromised device management policies. From a risk standpoint, posture is not a moral judgment about the user. It is an environmental fact that changes what an attacker can do and how confident you can be in local protections. In a testing context, you treat posture as part of the threat model, because what is safe enough on a well-maintained device may be completely inadequate on a device with weakened controls. Authentication on mobile often looks familiar on the surface, but the risks tend to cluster around token storage, session handling, and recovery workflows. Tokens are attractive targets because they are portable proof of authentication, and if they are stored insecurely, an attacker can replay them without ever knowing the password. Session handling issues can include overly long lifetimes, failure to bind sessions to device attributes, or a lack of server-side invalidation when the user logs out or changes credentials. Insecure reset flows are a common weak spot because they prioritize user convenience, and attackers are very good at abusing helpful pathways that bypass the main authentication check. If a reset process relies on weak verification, predictable codes, or insecure links, it can become an easier entry point than brute forcing a password. The lesson for Pentest Plus is to think beyond the login screen and consider how authentication state is created, stored, renewed, and destroyed. Beyond authentication, there are app weaknesses that show up again and again because they are rooted in developer workflow. Hard-coded secrets are one of the most exam-relevant examples because mobile binaries can often be inspected and strings extracted, revealing keys, endpoints, or embedded credentials that were never meant to be public. Debug features left enabled can expose hidden menus, verbose logging, test endpoints, or developer shortcuts that bypass security controls, and those paths can become permanent backdoors in production. Configuration mistakes, such as pointing a production app at a non-production backend, can accidentally expose weaker environments or data that is less protected. Even when the code is not obviously vulnerable, the build process can leak information through metadata, error messages, or unused libraries that expand the attack surface. The common thread is that mobile apps are shipped artifacts, and what you ship is what an attacker gets to study at leisure. To make these ideas concrete, consider a scenario where a mobile app stores sensitive data unencrypted on the device. Imagine an app that collects personal details, medical information, or internal business records, and it writes that content to local storage for offline access. The user experience might be smooth, but behind the scenes, the app could be saving full records into a plain database, leaving exports in a shared downloads directory, or caching responses in a way that other apps or a user with elevated access could retrieve. Logs might capture the same data during troubleshooting, and backups could replicate it to other locations without the user realizing the scope of exposure. An attacker does not need to defeat strong cryptography in this case, because the data is already in clear form at rest, waiting to be copied. This scenario highlights why storage risk is often the most direct path to impact. When you validate that kind of storage behavior safely, the goal is to confirm what is happening and document impact without causing harm. You would focus on identifying exactly which artifacts exist, what fields they contain, and what protections are present or missing, rather than attempting to exploit the situation beyond what is necessary to demonstrate risk. A responsible approach is to show that sensitive material is recoverable from local files, caches, logs, or backups under realistic conditions,
and then to clearly describe what an attacker could do with that access.
The most useful findings explain the scope of exposure, the persistence of the data, and the likely attackers who could benefit, such as someone with physical access, malware running on the device, or an adversary who obtains a backup.
Good documentation connects the technical observation to business impact, while keeping the testing footprint minimal and controlled. That balance is part of professional tradecraft and aligns with what Pentest Plus expects in reporting and ethics.
Mitigation starts with secure storage, because that is where many mobile issues either become manageable or become severe. Sensitive data at rest should be minimized, and when it must be stored, it should be protected using platform-provided secure storage mechanisms rather than ad hoc encryption routines.
Least privilege permissions reduce the damage of compromise by limiting what the app can access, and they also reduce privacy risk by avoiding unnecessary collection.
Strong transport security protects data in motion, but it also protects session tokens and prevents attackers from inserting themselves into client-server communication. Effective mitigation is rarely a single control, because mobile risk is a chain of dependencies that spans device, app, network, and backend services. The best approach is layered. Reduce what is stored, protect what remains, restrict access pathways, and ensure communications are authenticated and encrypted correctly.
There are common pitfalls that show up during mobile assessments, and one of the most important is focusing only on the device while missing backend dependencies. Mobile apps are often thin clients, and the real logic and data live behind API endpoints, identity providers, and third-party services that the app consumes. If you only analyze the local application package and ignore the server-side behaviors, you can miss authorization flaws, insecure direct object references, weak rate limiting, or misconfigured cloud storage that actually drive the highest impact. Conversely, if you only test the backend and ignore the client, you can miss how the app leaks tokens, misuses certificates, or stores data insecurely, enabling attackers to reach the backend as an authenticated user. The reality is that mobile security is an ecosystem problem, and your assessment needs to account for the full path from the user interface to the services behind it. Pentest Plus tends to reward that broader systems view because it reflects how real attacks succeed. Another pitfall is treating rooted or jailbroken posture as the only meaningful risk factor, when in practice many issues occur on fully standard devices. A well-maintained device still leaks data if the app caches sensitive responses, and it can still be vulnerable if the app mishandles certificates or stores tokens in predictable places. It is also easy to assume that a secure operating system automatically makes insecure design choices safe, which is a dangerous shortcut because platform controls are not designed to compensate for every developer mistake. On the other side, it is a mistake to overstate findings by assuming every user is on a compromised device, because that inflates risk assessments and weakens credibility. The best posture-aware analysis states how risk changes across different device conditions and then ties that to likely user populations and threat models. That kind of nuanced explanation is both professional and exam-aligned. Quick wins are often about reducing exposure rather than chasing perfect security, and mobile is a great place to apply that principle. Reducing stored data is a straightforward step because you cannot leak what you never keep, and many apps store more than they need for far longer than necessary. Tightening permission requests can often be done without redesigning the entire app, especially when developers switch to requesting permissions only when needed and providing clear user context for why access is required. Another fast improvement is to remove or disable debug features and ensure builds are produced with secure configurations that do not include test endpoints or verbose logs. Transport security can be strengthened by ensuring proper certificate validation and using modern protocols, which often yields immediate risk reduction for token theft and traffic manipulation. These wins matter because they reduce the attack surface quickly, even if deeper architectural work is scheduled later. To keep these concepts organized, a memory anchor can help you recall the core risk map: storage, permissions, transport, posture, and secrets.
Storage reminds you to look for local files, caches, logs, and backups that might expose data at rest. Permissions cues you to evaluate what capabilities an app requests and whether those align with legitimate use, because unnecessary privilege expands potential impact.
Transport points you towards encryption correctness and certificate handling, which determines whether data in motion is truly protected against interception and manipulation.
Posture makes you ask what the device environment allows an attacker to do, especially when integrity is reduced through rooting, jailbreaking, or insecure configuration.
Secrets ties back to hard-coded keys, embedded credentials, and leftover debug features that turn the shipped app into a treasure map for attackers.
As we close episode 81, the practical takeaway is a clear mental model of mobile risk that you can apply quickly. Track data, check permissions, verify transport, assess posture, and hunt for secrets that should not be in a client application. When you practice classifying behaviors, pick one observed app behavior and place it into that map. Then decide what the likely impact is and what mitigation reduces it most efficiently. If an app stores sensitive records unencrypted locally, you can classify it primarily as a storage risk, but you should still ask whether poor posture makes it easier to exploit and whether transport issues increase the likelihood of sensitive data being captured in the first place. That kind of layered reasoning is exactly what separates superficial testing from real assessment, and it is what a Pen Test Plus candidate should aim to demonstrate. By keeping the model consistent, you build speed and accuracy without relying on memorized checklists, and that is how you stay effective under exam pressure and in the field. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.